Hello AP Stat students, this is lesson 1.0 on data analysis. To introduce some vocabulary, a categorical variable places an individual into one of several groups or categories. Categorical variables are similar to hair color, eye color, political preference, religion, types of things that you would answer with a word, like my eye color is blue, my hair color is blonde, my political preference is independent, my religion is Catholic. Okay, a quantitative variable takes numerical values for which it makes sense to find an average. Quantitative variables are like weight, height, number of siblings in your family, age. So some of those values that you would answer back are numbers, okay? So you would say, I'm 12 years old, I weigh 90 pounds, I have 19 siblings, whatever your number answers are. Focus on who is being measured and what is being measured, okay, to answer these. So an AP exam tip, if you learn to distinguish between categorical and quantitative variables now, it will pay big rewards later. You will be expected to analyze categorical and quantitative variables correctly on the AP exam. A trick. What is an example of using numbers to describe the values of a categorical variable? A zip code is an example of a numerical kind of answer, but it is actually a categorical variable. And the reason why is because it can categorize you into regions that you're from. So there's two different zip codes that feed into this school. There's Spring Grove and there's Richmond. So if your zip code is different from someone else's, we shouldn't try to find the average zip code that comes to this school. We should instead categorize you as a Richmond or a Spring Grove address. What is an example of dividing the distribution of a quantitative variable into categories? So sometimes you have so many different ranges of or intervals of values that maybe you would chunk your intervals and try to treat the numbers as more of a categorical variable if it's age, or maybe spans of years if you're talking about years of cars entered in a car show. You might try to talk about the pre-war cars, which normally means pre-World War I, I think that reference is for. And then maybe like your muscle car era, so like your late 60s through the 80s. Okay, I'm kind of making that stuff up. I'm not so positive on those topics, but so maybe age range or span of years is going to actually turn into a categorical variable as well. But for the most part, these categories, categorical variable or quantitative variables, are quite distinct and separate. The distribution of a variable tells us what values the variable takes and how often it takes those values. The key is how often it takes them. Okay, the distribution looks at peaks and valleys across the variable and what that shape of that curve or graph or density curve looks like. All the above vocabulary is used throughout the year. An alternate example, the US Census data. Here's information from about 10 randomly selected US residents from the 2010 census. So here's each state that the person was from, the number of family members, their age, their gender, their marital status, their total income, and travel time to work. Okay. So across each row is an individual. Okay, so this is not necessarily already formulated data as far as compiling it and finding averages or finding anything like that. So far, this is just a table that is just delineating each individual's information. Okay, who are the individuals in this data set? There are 10 randomly selected US residents from the 2010 census. What variables are being measured? And identify each as categorical or quantitative. Categorical is the ones that have words, like what state they're from, what gender they are, their marital status, and quantitative is all the numerical ones, the number of family members, their age, their total income, and their travel time to work. Notice that we don't yet have a situation where we're using a value, like a quantitative variable, and we're moving it into categories because we're not categorizing anything here so far. We're not, we just have lists of individuals. So I didn't yet chunk age range. I didn't yet chunk any information like that and put counts of people that fall into those categories. I'm literally just putting every individual's information out so far. What variables are measured? Okay, describe the individual in the first row. For example, I'm just trying to humanize these numbers, and that's a lot of what AP Stats is actually trying to do. And it kind of gets a bad rap for trying to dehumanize and trying to turn values into statistics to help a cause. Okay, but no, we're not trying to do that at all this year. We're just trying to figure out, most of the time, we're trying to figure out if there's statistically significant evidence of some claim. But in the meantime, we are just talking about an individual. From Kentucky, 2 family members, 61 years old, female, married, total income of $21,000, travel time to work is 20 minutes. Okay, moving on to lesson 1.1. A data table lists the individuals, like the census example on the previous page. A frequency table displays counts or frequencies. So instead, I could say that I have like 2 people in the table that have this characteristic, and I have 7 people in the table that have this other characteristic. What is the difference between a data table and a frequency table? The data table shows each individual's data one at a time, while instead the frequency table collects the data of many individuals in each cell. A relative frequency table shows percents instead of just counts of people in each row. When is it better to use a relative frequency? When you want to compare distributions of different totals. So if I wanted to compare how many, the men in America and what their religion preference or religious beliefs are, then I could maybe compare that to the women in America and what their religious preferences or beliefs are. And then I can compare men to women, but let's say that this particular year that I'm drawing these comparisons for, that there's 2 million more men than women, or switch it, 2 million more women than men, but essentially there's a difference in the total count. Then when I compare counts of Christians and counts of Jews and counts of Muslims, I have to remember that overall, for every one of these comparisons, that there's 2 million total more of one gender than the other. So instead of comparing counts, I might want to compare percents, because then I'm comparing out of 100 for both genders, and I can more easily distinguish if there's actually a difference when I see a difference in the numerical values of counts. Okay, what is the most important thing to remember when making pie charts or bar graphs? Why do statisticians prefer bar graphs? The most important thing to remember is proper labeling. Everything needs a label. If you're doing a bar chart of some sort and you have slash bars and solid bars and polka dot bars, you need to put a key for all those different colors and what they stand for. If you're using axes, you have to label and scale your axes. Okay, you have to put a title at the top of the table. It takes a little bit of time to make a table. It will cost you points on the AP exam. Bar graphs are easier to make and compare and easier to make comparisons on than a pie chart is. Imagine trying to take a pie, right, and then divide it up by 360 for 360 degrees around, but then to say that you want to take 15% of it and 20% of it and 35% of it for some other category, and so you're going to break up all these categories. We have to keep figuring out how many degrees that is at a 360 and maybe use a little compass and things like this, protractor. So they're annoying. And imagine getting to the last part and not having the right amount of degrees left because you've cumulatively made very small errors just because your pencil has a certain thickness and all these other things. So pie charts, very annoying to make. We don't ever really make them because they're horrible. And so let's use bar graphs instead. Okay, when is it inappropriate to use a pie chart? When not all the parts of the whole are present. Okay, so what are some common ways to make a misleading graph? Is a pictograph, something like this below, okay, or something 3D. So if I was to set out little cars images and little truck images to stand for how many cars or how many trucks have passed me in the last 5 minutes on my little run in the neighborhood, well, trucks might be longer than cars. So if I only passed 2 trucks, but if I passed 4 cars, but my truck image is longer than my car image, the 2 trucks might take up more space than my 4 cars, and it will look as though I passed more trucks than cars. But really, I passed more cars than trucks. Also, if you use some sort of wide, some rectangle shape, and you just lock the ratio of width to height, and then you expand it because you need more height, and you expand it because you need more height, well, the width is expanding by a lot and the height's only expanding by a little. So if you have some data like this, and I'm not even that quick at reading this, 56 channels maybe, 81 channels and 95 channels, 56 to 95 is not as great of a difference as this seems. This makes it seem like 95 is like 5 times the amount as 56 channels, but it's not. It's just roughly double. Okay, not even quite double. And it looks like 81 channels is double the channels of 56 channels, but it's not. It's only like almost 50% more of it. Okay, so that's strange. So these 3D types of graphs are no good, or these like rectangular graphs. So also bad is not starting the frequency axis at 0, but if you were to skip and to just accentuate the difference between bar heights. So what this means is, take my lead teacher meeting notes here with my T stain on it. Okay, so let's say that you had some difference and let's just say that some bar heights were 15 and like 18 and then like 20. Okay, so then take that, but now instead scissor this and start at 15 and now say that one bar height is here, another bar height is here, and the last bar height is here. This is a misleading graph because it makes the one bar look like it is 5 times bigger than the other bar, but really it's just a little bit higher if it is from 15 to 18 to 20. Okay, 15, 18, 20. But here it looks like there's almost no people here and all the people here, or whatever object this is. Okay, so we need to make sure that we don't make this jump. On histograms or bar graphs, okay? And you'll see that shortly. Now, later in the year, we're going to talk about, actually very soon in the year, in a week or so, we're going to talk about scatter plots. And some scatter plots have information, especially if years on the bottom axis. Okay, say that we start in the late 1990s and go into the 2000s, like 2000, 2005, 2010. And then I have all sorts of data of like pounds of oranges that some company sells. So I've got something like 1,000, 1050, 1100, 1150, different weights of oranges in their big orange crates. I don't know. So anyway, we're going to have all sorts of companies that sold these different crate sizes of oranges throughout the years, and we see a trend that is, as the years go on, that these orange crates tend to be heavier, or something like that. Well, it wouldn't make sense for me to start this at 0, 0, and for me to go all the way out to the 2000s, okay? And then for me to go from 0, 0 all the way up to the 1000 mark, and then for me to just have a little tiny clump of points like that. Okay, so in a scatter plot, it does make sense to narrow in your window and to blow up this image so that we can actually see a pattern and see the clumping, okay? Because if we're zoomed out enough, this might just look like a little clump out there, look like a little ball of points. But if we're zoomed in enough, we can start to depict maybe some sort of linear kind of trend here, okay? If not a strong linear trend, then maybe a moderately strong or moderately weak linear trend. So anyway, scatter plots, go ahead and zoom in. These bar charts don't make that jump. Okay? All right. Very good. What else can I say? Okay. So that's that point right here. Don't make your bars of different widths. Okay? This picture's bad. It's misleading. And that's because our eye tends to follow and be drawn to the whole area of the bar. And so we must keep our bars of equal width. Okay, what's wrong with the following graph then? It violates the area principle. Okay, the principle that our eye tends to see area, not just height. It makes a DirecTV look twice as big as Dish Network, and but it's only 14 units more. 15? Okay. Okay. Cable, Dish, DirecTV. Oh, right there. Okay. So that comparison right there. All right. Turn the page. What is a two-way table? A two-way table describes two categorical variables with two or more different levels of those variables. So a two-way table has different categorical variables. Like here I'm using age this time as a categorical variable, and I'm chunking it, and I'm not just listing out each individual and their data values. Here I'm using a frequency table, and in this frequency table I'm showing counts of people in this row, and counts of people in this row, and this row, and this row, not just a person and their data like we saw in this data table. A single person's data. Well, now I take huge amounts of data and I take 2,024 people and I include them somewhere in this inside of these of this table, somewhere in these 9 squares. Do they have an iPhone, an Android, or other? And what age are they? Okay, so then I have these totals over here and these totals down here and this total. Okay, the Pew Research Center asked a random sample of 2024 adult cell phone owners from the United States which type of cell phone they own, iPhone, Android, or other, including non-smartphones. Here are the results broken down by age category. The marginal distribution of one categorical variable in a two-way table of counts is the distribution of values of that variable among all individuals described in the table. So this marginal distribution is the distribution of age, and it only describes age because I have 517 18-34-year-olds. I don't know anything about their phone preference. 637 in this age range and 870 in that age range. Or the marginal distribution of phone usage ignores age and instead just describes all the iPhones, all the Androids, and all the other users. Okay, so marginal distribution, I tend to think of what the margins of the page are, and the margin is on the outside of the page. You tend not to write in your margins, kind of like the margins of a printed page. Up here, over here, okay? Unless you're like me and you need the margin space to do little activities. Okay, but the margins are generally that outside area, okay, where there's no printing. So the margin is this outside area of the table where we list our totals. All right, that's called our marginal distribution. Cell phone example. Calculate the marginal distribution in percent of the type of cell phone. Then I wanted to calculate these percents. Okay, iPhone, there's 467 out of 2024 people. That's 0.231, so 23.1%. Android, 530 out of 2024 people use Androids. That's 0.249. And other, 1054 out of 2024 is 0.521. Make a graph to display the percent and describe what you see. So iPhone 0.231, Android 0.249, and other 0.521, or 22.1%, 24.9%, and 52.1%. Okay, I'm going to talk about that right now. If you notice, all three of these percents add up to 100.1%, and you're like, shoot, I put all that work into finding those percents, and now it adds up to more than 100%. What do? You do nothing. It's called round off error because of just the unique way that these numbers with that total, and when you divide out of that total and you round to the thousandth place, that they give you one extra thousandth place, or 10,000th, or whatever place this is, like 1.01, so thousandth place. Anyway, so that's just fine. Okay, there's a name for it, but we leave it. Okay, so don't try to fix it. It is not actually a problem. Okay, over here, iPhone, Android, other, and then I list them up by percent, and I have labels, and I have an axis scaled, and I have a label, and I have a title. Very good graph. iPhone, let's see here, describe what you see. iPhone and Android makes up similar percents of the total cell phone usership. However, other makes up more than half the usership, more than iPhone and Android together. Okay, so that's what I'm describing over here is the uniqueness. I try not to talk too much when I describe what I see. I try not to talk too much about similarities. Focus on the differences. Try to really elaborate the differences. If you mention a similarity, try to spend twice the amount of space talking about the differences and exaggerating them, okay? We really, really want to see where are there categories that are different from the other categories, okay? So we see other is quite different. Talk about that, okay? What is a conditional distribution? How do we know which variable to condition on? A conditional distribution describes the values of that variable among individuals who have a certain characteristic of another variable. Okay, there are two conditional distributions for every two-way table. Identify the explanatory variable, then separate the categories of it and divide each category by the total. So for the cell phone example, calculate the conditional distribution of cell phone type for different age groups. For different age groups, age is the explanatory variable. Age seems to come first. Then comes their cell phone preference. So first, someone is generally young. Yes, 30-year-olds are young. Okay, then they use a cell phone type. Then somebody's middle-aged. Then they use a cell phone type. Then somebody's elderly-ish, and then they use a cell phone type. So we'd say age comes first, then after you're a certain age, you have a certain preference because of your age. Okay, that's at least the hunch. You don't get a certain preference of cell phone, then become younger, or get a certain preference of cell phone, and then magically become older. Okay, so let's go ahead and take then out of the 18 to 34-year-olds, how to find the conditional distribution. You identify that these are the explanatory variables, and then you separate them into each unique explanatory variable one at a time. Take a look at your 18 to 34-year-olds. Take 169 out of 517, 214 out of 517, and 134 out of 517. Then do the same thing for your 35 to 54-year-olds. Take each of these and divide them out of the total. Do the same thing for 55 plus. Take each of these and divide them out of the total. So here, for just a couple, I showed you the division just so that you can establish that pattern. 169 out of 517, 214 out of 517 are these two squares being divided by the total. So now you can see that I'm dividing down, and what I mean by that is it's a visual thing here. I'm just trying to find words to describe that I'm dividing in this downward direction as opposed to dividing across. I'm not dividing 169 by 467, 161, and 127 by 467, okay? I'm dividing by this in this vertical sense because I identified that the age is the explanatory variable, so I'm going to separate each of them and divide and find percentages. So I find that for my 18 to 34-year-olds, that 32% of them use the iPhone, 41% use Android, and 25% use other. So the most use is on Android. Of 35 to 54-year-olds, I see 26%, almost 27% use iPhone, 29% use Android, and 43% use other. So now we see it shift, right? We see much more people jumping over to other, and iPhone usage went down, and Android usage went way down. Now let's talk about the 55 plus. Android usage went down again, okay? Android went down again, and other went way up, okay? So that's how I can make comparisons. Yes, I want to compare across. I want to compare what my young do to middle-aged to older, but I can't divide across then. You need to divide down so that you can make the comparisons across. Does that make any sense? It's really confusing, isn't it? Which way do I divide is always a big question. Try to first identify your explanatory variable. Second, section out each explanatory variable one at a time, each level of the explanatory variable one at a time, and then divide in the viewing area. Okay, divide in the direction that the explanatory variable faces. So if your explanatory variable is across the top, then maybe it's facing downward, okay, and you're going to divide down. Okay, segmented bar graphs. You must use percents. These graphs are hard to compare. These graphs make it hard to compare categories, and it's also called a stacked bar graph, and it needs a key. So here's how you make a stacked bar graph, or a segmented bar graph. You list your explanatory variables, then you divide up how they use cell phones. So first, my 18 to 34-year-olds, 32% used iPhone, so just about 30. 41% used Android. Now I have to count from 32, add 41 to it, and I get all the way up here around 73-ish, just about 74-ish. So that's where that line is supposedly. And then other is the 25.9%, almost 26% up there. Okay, so then I do the same thing for my 35-year-olds, 26% and 29% more, and then 43%. And then 14%, and then 11-ish%, and then 73%. Okay, so that total, they all stop at the 100. Okay, and then I have to make a key. So let's talk about the characteristics of the graph that give you full points. Accuracy, sure, okay, or if you made errors up here, at least those errors are, you know, this table's related to that perfectly. Okay, also labeled, scaled, title, key for, you know, striped, plain, and solid. Okay. Why are segmented bar graphs good to use? Why are they bad? They're good because they closely match the structure of a two-way table, the explanatory versus the response on the XY axis. They're bad because they're hard to make comparisons. So sure, in this one, we can see the use of other has increased drastically, but I can't really compare numerically if I didn't have a table here. I can't compare how much this shrunk by because it's really hard to go across here and quite subtract and get that percent quite right, okay? So these middle areas are hard to compare, plus this middle area starts here and only goes to here. This one starts at a different height. It almost starts where it ends. So yeah, I can visually see that this is smaller, bigger, biggest as far as the white areas go, but it's really hard to compare perfectly, okay? So if they all start at the same point, like this, then I can just compare heights and I can compare more easily. Okay. What does it mean for two variables to have an association? It's the same thing as two variables having a relationship. We say that there is an association when knowing the value of one variable helps you predict the value of the other variable. For example, if knowing that a person is male makes one of the responses more likely, there is an association between gender and response. Give two examples of graphs, one with an association, one without an association. one with no association, one with an association. Okay. All right, so say that males and females who invest in retirement looks like this. They do invest, they don't invest. Females do invest, don't invest. Well, is there a difference between males' investment patterns and females' investment patterns? No. So is there an association between gender and investing in retirement funds? No. There's no association, and here's why. It doesn't matter if you're male or if you're female, you have equal likelihood of investing in your retirement. It doesn't make a difference if you're male or female. So knowing a person is male tells us nothing more about their investment likelihood than knowing that they're female tells us about their investment likelihood. They're both as likely to invest or not invest, and so we might as well just put them together and say that people are this likely to invest in retirement. Okay? An association instead means you have different bars or percents amounts, and they are then dependent or not independent, either phrase you like. So all these things mean the same thing, okay? Or that's what the visual will look like, but association and dependent mean the same thing, and no association and independent mean the same thing, okay? So dependent means that there is a relationship between your gender and your likelihood to invest. So let's say that this is male's likelihood to invest. They aren't big investors. Let's say this is female's likelihood to invest. They are big investors, or switch it around. Females, males, either way. And so we could say that there is an association between gender and the likelihood of investment, because if we know that a person is this gender, we know that they're less likely to invest. We know that if they're that gender, they're more likely to invest. Okay? How can you tell by looking at a graph? Okay. If you go to too many bars, your sins will add up. Okay. What did I mean by that? I don't know. Well, if I think of that, I'll come back to that. Okay, the cell phone example. Explain what it would mean if there was no association between age and phone type. Knowing the age of a person does not change the likelihood that he or she owns one type of phone versus another. Based on the graph, is there an association between age and cell phone type? And justify. The graph we made on the previous page. There is an association between age and cell phone type. We see that the 18 to 34-year-old, 35 to 54-year-old age groups prefer iPhone and Android phones because more than 50% of these age groups own these phone types. However, for the 55 plus age group, only about 26.1% of this group uses iPhone or Android, which is 30% less than the 35 to 54-year-old age group and 48% less than the 18 to 34-year-old age group. Notice that the graphs do not imply cause and effect. However, women who wear bikinis to the beach are less likely to have gray hair. Want to avoid getting gray? Wear a bikini. So this is kind of just a fun little pun. The graph itself describes an association, but it doesn't describe cause or effect. People aren't getting older because of the cell phone that they choose. Okay. Same thing with women. If you go to the beach and you wear a bikini, you're probably younger, okay? Probably. You probably don't have gray hair. Now, women at the beach with gray hair tend to wear one pieces, okay? But if you wear a bikini, is it going to make your hair less gray? Is it going to make your skin less wrinkled, sag less thin? No, it's not going to do any of those things to your old lady skin. So we can't do cause and effect, but we can say that there's an association with swimsuit preference and age. Okay, all right guys, thank you.